Welcome back to nuclear physics. Let's review a little bit from last time. The nucleus is like a package of jelly beans tightly crammed together. True or false? And you think it is? Well, okay. Yeah, it's true. That's just what they look like, a package of jelly beans. Beta minus decay is when a nucleus does what? The answer is it turns a neutron into a proton. You can tell because it's called minus decay. That means an electron comes out. If an electron comes out of the nucleus, then something inside has to become positive, and the only way that can happen is for a neutron to become a proton. Beta plus decay is when a nucleus does what? Well, that's the flip side. That's when a proton turns into a neutron. That positive charge has to go somewhere, and it comes out as a positive electron called a positron, the antiparticle of the electron. Gamma decay in a nucleus occurs when a nucleus does what? And that's just like atoms. Emits a photon going from a high energy state to a lower energy state, which in the nucleus usually looks like a higher mass state to a lower mass state. E equals mc squared. Alpha decay is when a heavy nucleus does what? Well, it must be the only one that's left. So yeah, that's when it emits a helium nucleus. And we'll talk a lot about that before the time's up. In a certain decay, we have magnesium 23 going to sodium 23 plus something. This is an example of what kind of decay. Okay, well, so 23 to 23, that means neutron and proton numbers stayed the same. But 12 to 11 on the bottom means that a proton disappeared from inside the nucleus. Can't really disappear. Its mass is still there because 23 went to 23. So what happened was the positive charge of the proton left the nucleus, and that means a positive charge had to come out, and that's the positron, and so this is beta plus. All right, this is going to be kind of a grab bag today. Little of this, little of that, and ending with nuclear reactions. Okay, so we have done experiments on nuclei for a long time, and these are the results of shooting very high energy electrons at nuclei and watching the way the electrons scatter. And from those experiments, we can tell what the density of the nucleus looks like. It's kind of flat in the middle. That's where the highest density is, at the center of the nucleus. And then it has a fuzzy edge. It's not like those pictures where they have hard edges. They're fuzzy edges. Well, it's quantum mechanics, right? It's got to be fuzzy. Just like electrons live in fuzzy clouds of probability, neutrons and protons live in fuzzy clouds of probability. Although these are quite a bit more localized and more like particles than electrons, than atoms are. The electron clouds around atoms are. But still, they do have fuzzy edges, as quantum mechanics would suggest. There is a nuclear periodic table, just like there's an electron periodic table for electrons arranged around positive nuclei. But the energy levels are not simple, like they were in the case of the hydrogen atom, minus 13.6 CV over n squared. Every proton and neutron that goes into the nucleus changes the energy of the nucleus significantly and makes brand new wave functions, and so it's really complicated. But just sort of to get a feel for it, we're going to talk about the first two. So this is hydrogen. Let's talk about all the ways you can make hydrogen. The simplest way and the most abundant way is to just have a proton. That's 1H1, and most of the hydrogen in the universe is in this state. But that's not the only way. You can also put a neutron together with that proton, and that's 2H1, or heavy hydrogen, deuterium we call it. It's 0.016% of the hydrogen in the water of the ocean and on the rest of the planet. So that's a big enough percentage that you could actually get this out. And we have. You can buy deuterium, and you can buy water that is what would it be? D2O instead of H2O. Tritium is a little trickier. That's where you put 2 neutrons in with a proton. 3H1. You could call it extra heavy hydrogen. There isn't any of that naturally on the Earth because it has a half-life of about 12 years before it decays. But we can make it in nuclear reactors, and we do make it in nuclear reactors. It's useful for doing experiments, and it may someday be useful as part of the fusion energy business if there ever is one. You could imagine putting 1 more neutron in, so you'd have quadrium, proton and 3 neutrons. But we just don't talk about that because you can make it in particle accelerators, but it lasts for about 10 to the minus 22 seconds, so nobody cares. If we now go to helium, you could imagine just sticking 2 protons together. The strong force is supposed to be strong after all, and should be able to glue 2 protons together, but it just doesn't happen. You can't even find this in experiments. You just can't do helium this way. But if you put 1 neutron with it, that's enough to space things out and make helium-3, which is stable. And we find helium-3 in the natural helium that occurs on the Earth. If you put 2 neutrons with 2 protons, oh, the nucleus loves that. That's like a nuclear noble gas. That's a very low stable energy state. And most of the helium that we find is of that kind, helium-4. You could put another neutron in there to make helium-5, but it's unstable and only lasts 10 to the minus 21 seconds. So that means there's only a narrow range of neutron numbers that you can put in these atoms, and that turns out to be true all the way up the periodic table, although when you get to higher numbers, there's a wider range of neutron numbers that are stable. Well, what goes wrong? Why are some nuclei unstable? Well, there's 2 reasons. There might be too many protons. You have too much electric repulsion then, and the nucleus would be happier if one of those protons wasn't in there. And so the proton turns into a neutron, kicks out an anti-electron, and goes to a happier state. Or it can just refuse to form in the first place. You can also have too many neutrons. With too many neutrons, the nucleus can tell that it can go to a lower energy state by either kicking the neutron out or, more likely, having the neutron turn into a proton. That's normal beta decay, beta minus decay. And so between those 2 bounds of too many protons, too many neutrons, there's a stable range, and that's where these isotopes exist. So really, the neutron can go to a lower mass state? Well, yeah, it can. So here are the masses of protons and neutrons, and they agree in the 1 place and in the 0.6 and the 7, but in the 3rd decimal place, the neutron has a 4 and the proton has a 2, or if you rounded it, well, if you rounded it would be a 5 and a 3. Anyway, the neutron has more mass. And this means that if you put a neutron all by itself, like hang it out in the air and just let it sit there, it's unstable. In about 10 minutes, it turns into a proton, kicks out an electron and an antineutrino. It's beta decay. It's the exact same thing that muons do. And this is just an example of, you can think of the neutron as being a high energy state of the proton, although that's not quite accurate, as we'll see next time. And it can decay to that lower energy state. So you'd think maybe, hey, look at that on the right side of the equation. You got a proton and an electron. They ought to be able to get together and make a hydrogen atom, right? Well, no. There's a lot of energy released in this decay, about 1 million electron volts, and it's mostly picked up by the electron. So the electron goes screaming off, with about 1 MeV of kinetic energy. And so this doesn't make hydrogen. This is an explosion, and the pieces go all over the place. Here's a picture of the stable nuclei. So proton number goes along the bottom, and neutron number goes along the top, along the side. And if they were equal to each other in all these nuclei, that's the black line, n equals z, you can see running across the graph. Down at the low end, that's a pretty good approximation, that straight black line is, to the blue range. So pick a z, like maybe z equals 3 for lithium, way down there on the lower left-hand corner. And if you go up, you'll see there's a blue range of isotopes from just below the line, where the neutron number is low, to just above the line, where the neutron number is higher. And those are stable isotopes, and everybody's happy. But as you go to higher proton numbers, you have to have more neutrons to keep the nucleus happy. But you also notice that the range gets wider. So we saw last time, you look at something like mercury, it's got like 9 stable isotopes. And then way up there, you see where the black, you have little black squigglies going up there. Those are the stable isotopes. And when you get up to about a Z of 82, then there just aren't any more black squiggles. There are no more stable nuclei above lead at 82. That seems odd because between 83 and 92, those are elements that we can dig out of the ground. They're here, so why aren't they stable? Well, they are stable, but their decay times are billions of years, and the Earth's only about 4 billion years old, so they're still around from when the Earth formed. But if we wait long enough, they'll be all gone too. There are some magic nuclear numbers. Just like the filled shells that make the noble gases in the periodic table noble, way over there on the right side of the periodic table, you have helium and neon, argon, krypton, and xenon. They're very unreactive because they're very stable. They just don't want to share electrons with anybody else. Well, a similar thing happens in the nucleus, where the protons and the neutrons just settle into a filled shell state, and they're very happy. And those magic numbers are 2, which is helium. So helium is doubly noble. Its nucleus is noble, and its electron configuration is noble. And then you have kind of funny looking numbers, 8 and 20 and 28 and 50 and 82, which makes oxygen, calcium, nickel, tin, and lead be noble nuclei because they have filled shells. High energy levels in atoms are unstable, and they solve that problem by having the electrons drop to a lower energy state and emit a photon. We're used to that now. It looks like this. There's a high energy state on the left with lots of wiggles, goes to a lower energy state on the right with not so many wiggles, and a photon comes out. High energy or high mass states in nuclei are also unstable, and they emit stuff so that the nucleus can go to a lower energy state, but they can emit more stuff than just photons. Although the decay looks very similar to what happens with photons. Here's beta minus decay with all the details shown. You have a neutron, which consists of 3 quarks. It emits a W minus boson, which allows one of the quarks to turn into a different kind of quark, and it kicks out an electron, and the neutron becomes a proton. The W minus only lasts for like 10 to the minus 20 seconds or so. So the W minus that's emitted, like the photon that's emitted in an atom, it very quickly changes into something else, and the something else is an electron and an antineutrino. But that's what the nuclear decay for beta minus looks like. It's pretty similar, except for the W minus decaying to what happens in an atom. But that's not all that can happen when a nucleus decides to go to a lower energy state. It could emit positrons, that's beta plus decay. It could emit a gamma ray, that's like that's a photon. That's like what happens in atoms. Or it could kick out an alpha particle. So there's lots more ways than in atoms, and it makes nuclear physics be a little complicated. So here's another quiz question. True or false? A neutron in a nucleus has kinetic energy. What do you think? Well, it's true. A nucleus does have kinetic energy. It's moving around in there all the time, even though it's a bag of jelly beans. The neutrons, that's dynamically, that's a bad picture. They're very fast-moving jelly beans. It's more like jelly beans in a blender down inside the nucleus because they're moving pretty good. Okay, let's look at a decay example. Here's the decay example using plutonium. Plutonium-238 is an alpha emitter, kicks out alpha particles, has an 88-year half-life, turning into uranium-234. You may have encountered this substance in the movie The Martian, when Matt Damon is talking about the RTG and how it's hot and dangerous. Okay, well, that's because it's full of plutonium-238. And each reaction, alpha reaction that occurs in there, releases 5.6 MeV of energy. But look, why isn't it a beta plus emitter or a beta minus emitter? Well, let's take a look. To be a beta plus emitter or beta minus emitter, it would have to go to americium-238 so that its proton number could go up by 1. That's that one right there. Now check the masses between the original plutonium and the americium. The americium has a 5 in the second decimal place. The plutonium almost has a 5, but not quite. So it can't go. It can't decay this way because the end state has more energy than the starting state, so this wouldn't go. Here's beta plus decay down here, and it's too high too. It's got a 5 in the second decimal place. But if you look at the final state of the alpha decay, which is uranium-234, you take its mass plus the mass of the helium nucleus that it kicked out and add those up. They add up to 238.044, and that's lower in the third decimal place than the 49 that the original state had. So this is the one that can go. So we have to cross out beta minus decay, cross out beta plus decay, and we get alpha decay. That's the way plutonium loses its energy. When North Korea was claiming to the world that they had a nuclear weapon, people mostly didn't believe them. They thought they were just making it up. So to prove that they did, they invited a U.S. delegation of nuclear scientists to go over there and look at what they had. Now, they didn't give them a full tour of everything, but as part of the tour process, they let these scientists come into a room, and somewhere in the room on a stand there was a piece of gray metal about the size of a baseball, which they claimed was bomb-grade plutonium. Sig Hecker, former director of Los Alamos National Laboratory, asked them if he could hold it. They looked at each other kind of funny. They knew about radioactivity. They wouldn't hang around radioactive stuff if they could help it. But they said, yeah, I guess if you want. And so he went over and he picked up this 5-kilogram baseball, very heavy baseball, and he immediately knew it was the real thing. He knew it was plutonium. How did he know that? And why did he do this dangerous thing? Well, he didn't ask to lick it. So here's something you should know about alpha particles. Alpha particles are big and fat. They're great big honkin' helium nuclei, not little zippy electrons. They don't penetrate the skin, at least not the dead layer of the skin. They don't even penetrate paper or a coat of paint. It's okay to hold an alpha emitter, but don't eat it. The alpha particles that will get into your cells, or at least the plutonium or whatever is emitting alphas, those will get into your cells and they'll emit alpha particles. And then there's no protective layer. The high energy alpha particle bullets will wreck the genetic machinery of your cells and cause cancer. So don't eat it, but you can hold it if that should ever happen to come up, which I doubt that it will. Okay, let's look at some radioactive decay examples. So here's one. This is another plutonium example. This isn't the same stuff that Sig Hecker held in his hand. He wouldn't have wanted to hold this stuff. This is plutonium-238, which is also an alpha emitter, but its half-life is only 88 years. And so it's sending out alpha particles way faster than what Sig Hecker held. And it gets so hot that it glows red hot. This is an actual photograph of a little button of plutonium. It's actually plutonium dioxide, which is kind of like a crystal, like salt, sort of. And it's much more stable to handle. Doesn't get spread around as much as the metal does. And so this is the form it's usually used in RTG, in an RTG, which is a radioisotope thermoelectric generator. It's just a bunch of hot stuff being heated by its own radioactivity, and with very low efficiency, that high temperature thermal energy is converted into electricity. But if you're on a spacecraft and you don't want to have moving parts that you can't fix, this is an okay way to generate electricity. Here's a beta minus emitter. It's carbon-14. We talked about that last time. 5,730 year half-life, turning into nitrogen-14, and it's good for radiocarbon dating. Here's a beta plus emitter, carbon-11. You can make carbon-11 in a nuclear reactor, and it has a 20-minute half-life, and it puts out positrons. Positrons are very handy for medical detection, and carbon is a really good element to use biologically because our bodies like carbon. And so what you do is you make some of this stuff. You have to pretty much have a nuclear reactor right on the site, very nearby. You hustle some of this stuff, after you isolate it, you hustle some of this stuff over to the medical facility, and somebody drinks it. And this carbon, in whatever form they put it in, so that it goes somewhere, maybe some sugar or something, so that it goes to the right kind of cells. It then sits in those cells and emits these positrons. And when a positron comes out, an anti-electron, pretty much the first thing it sees is another electron, which is a normal electron, not an anti-electron. And when two antiparticles meet each other, they annihilate each other and send out two gamma rays at very precise energies, 0.511 MeV gamma rays. And you can detect those gamma rays and follow their tracks and figure out where they came from. And you can figure out where this carbon, radioactive carbon you put in the person's body is, and that it helps with medical diagnostics as long as you don't use too much of it. Okay, let's look in detail at this plutonium-239 that Sig Hecker held in his hand. We're going to calculate how much power was being generated in that 5 kilogram baseball. You have a homework problem like that, like this. That's why I'm doing it. Just to put all of the variables in that you might encounter, I'm going to have it be plutonium dioxide instead of pure plutonium metal, just so that you see what happens when you have to mix two different kinds of elements together. All right, so here's what we need. Here's the plutonium mass in atomic mass units, 239.05, 2163. Uranium is 235.04393. Helium is 4.002603. And oxygen is 16 atomic mass units. First thing you need is to know how much energy is given off in each decay of a plutonium nucleus. So you go to Wikipedia and you look it up, and it's 5.16 MeV. Of course, there's a long way around here, which is to subtract the products from what you had initially. But if you do that, you get 5.16 MeV. The next thing you need to know is what the decay rate is. How fast is this happening? Because power is energy per time, so you need a per time thing, which is the decay rate. How many decays per second? That's the log of 2 divided by the half-life. So we take 0.693 log of 2 divided by 24,120 years, 365 days in a year, 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute to get it in seconds. This turns out to be 9.11 times 10 to the minus 13 per second, which is such a small number, it seems like it shouldn't actually count for very much. But there's a lot of plutonium. There are a lot of plutonium nuclei in there, which compensates for this small rate. So we need to know how many. The plutonium dioxide atomic weight is 239.05 plus 2 oxygens. Well, let's add a 32 to this. Is 271.05. And this comes out conveniently in grams per mole. So if you want to know how many moles you have, you just take 5,000 grams of this stuff, divide it by 271.05, and you come up with 18.4 moles of plutonium nuclei, because every plutonium dioxide molecule has one plutonium nucleus in it. We now use Avogadro's number to find out that we have 1.1 times 10 to the 25 nuclei. Okay, finally, we can do it. We want to know, if we knew how many nuclei were decaying per second, we could then combine that with the energy per decay, and we'd know the power. So we need dN/dt. We have an equation for that. It's in your book. We saw it last time. It's in the chapter summaries. dN/dt is minus lambda n. So we take minus the lambda that we found times 1.1 times 10 to the 25 nuclei, and we get minus 1.01 times 10 to the 13 nuclei per second. And finally, we can find the power, because the power is the rate of change of energy. So that's the energy in each decay times the number of decays per second. And you multiply all those numbers together, and you get 8.35 watts. That's enough power to make something feel warm. If you had an 8-watt light bulb in your hand, it would be warm. The RTG in the Martian movie has a plutonium isotope with a half-life of only 88 years. So that makes a lambda that's 270 times bigger, which would generate 2.3 kilowatts. You don't hold 2.3 kilowatts in your hand. That's going to be very, very hot indeed. And it actually makes the material glow red hot. Okay, let's do a little quiz here. Uranium-238 decays by alpha decay. Which one of these is the correct decay scheme? Let you think about that for a minute. 2, 3, 4. Okay, so it's an alpha particle is 4 atomic mass units and 2 units of charge. So you want to see 238 go down to 234, and the 92 go down to 90, and so that's D down there at the bottom. Nitrogen 12 is a beta plus emitter. Which one of these schemes is correct for beta plus decay? Okay, so it's got to be one that shoots out a positive electron, a positron. So that eliminates C. You need the mass number to stay the same, because all that came out was an electron and it hardly has any mass. So that eliminates A. So it's either C or D. Oh, let's see. No, it's either B or C. B or D. Oh my gosh. It's either B or D, because they go 12 to 12. 12 to 12. They both go 7 to 6. That's right, because what happens when the plus comes out is that a proton changed into a neutron. But the only way they differ is that one has an antineutrino and one has an ordinary neutrino. So how do you decide which one? Well, you don't know this yet. It's D, and here's the rule. Antimatter and matter must balance on the right side for the electrons and the neutrinos. So B can't be right because E plus is an antiparticle and the antineutron, neutrino, is an antiparticle. And that's two antiparticle-nesses on the right. You can't have that. You have to have normal and anti for it to go. And so it's D. And we're going to talk about that some more next time. Okay, let's talk about how alpha decay works. In a nucleus, the nucleons are stacked in energy levels in a deep well. At the top of an alpha emitter, there will be two protons and two neutrons that in their states in the nucleus, they kind of hang together as two protons and two neutrons. They like to do that because that's called a helium nucleus, and it's a very stable particle. They'd really like to be an alpha particle. These four nucleons will be up near the top of the nuclear energy well for heavy elements, getting up to the point where the elements won't even be stable anymore. If you're up on that end of the periodic table, up approaching uranium, then these four nucleons are almost ready to come out. But the strong force is still holding on to them. But if somehow they could get away from that strong force for just a little bit and magically move outside the nucleus, then they wouldn't feel that strong force anymore. They'd be a positive particle next to a big fat positive nucleus, and they'd be repelled away. So it looks kind of like this. That red curve is potential energy. And so you can see the deep square potential energy well that the nucleus has on the left. And then you can see the high potential energy and then the potential energy going down like 1 over R. That's the electric potential energy on the outside. Now we're going to start filling this up with protons and neutrons. So here they come. We fill them up, we fill them up, we fill them up. We get up near the top, and those four guys at the very top can kind of imagine being outside. They can't get there because they have to go over an energy barrier, but you know what's coming. We discussed this a couple of times ago. So that alpha particle at the top is both in the nucleus and outside the nucleus simultaneously. It's like Schrödinger's cat. It's tunneling, and so it's there, and it's there, and there is a finite probability that it would just show up by tunneling outside the nucleus, and once it does show up outside the nucleus, it's out of here. It's a positive particle next to a positive nucleus, and away it goes. It's just gone. So the alpha particle tunnels out before the well gets completely full and can't hold nucleons anymore. And that's why the last 10 or 11 elements or so beyond uranium or beyond lead aren't stable. The alpha particles can tunnel out of them and they're radioactive. Tunneling varies by enormous amounts depending on how big of an energy barrier the alpha particle has to tunnel through. And that accounts for the large range of radioactive half-lives in alpha emitters from a microsecond to longer than the age of the universe, just depending on how high and wide that energy barrier is. Okay, here's a final note about alpha particles. We can obtain neon, argon, krypton, and xenon, those four noble gases, simply by cooling air until these gases condense out. That's done all over the country. It's done on Geneva Road around here, down at Air Liquide. But we can't get helium this way. Helium is so light that its random thermal velocities are high enough. You know the distribution of velocities curve we saw, where there's a long tail of high energy particles in a gas, the distribution of speeds in a gas. Well, the helium velocities at the top end are high enough that they can escape Earth's gravity. And so helium is just evaporating out of the atmosphere all the time. If you release helium, that helium balloon that you let go, I'll tell you what happens to it. That helium balloon drifts away. It goes up in the foothills and it gets caught in a piece of oak brush that's probably been burned and is all scraggly and has sharp branches sticking out. It hangs up in there so that hikers like me can go up there and walk off the trail and pick the thing out of the trees because it looks terrible. It sits there before somebody finds it, and it pops, and the helium is released into the atmosphere, and the helium atoms just mix around in the atmosphere. They're light, and they have a tendency to go higher and higher in the atmosphere because they're so light. Pretty soon they get up near the top of the atmosphere, and some of their random velocities are high enough that they can leave the Earth's gravity, and we're just leaking helium into space all the time from helium balloons. So if you can't get it out of the air, where does it come from? How do we get helium to put in helium balloons? The answer is it comes out of the ground with natural gas. And why is it in the natural gas? Well, the methane has been sitting down in the rocks for a very long time, long enough for radioactive minerals in the rocks to put out lots of alpha particles, which slow down in the rock, pick up electrons, and become helium gas. And then the helium gas joins the methane gas, just waiting for somebody to punch a hole into the gas reservoir and let them both out. There are nuclear reactions, just like there are chemical reactions. There are nuclear reactions. If you take two atoms, shove them together a little bit so that their electron clouds touch, they might rearrange and form a new kind of electron orbital, and that's what's called a chemical bond. So a similar thing can happen with nuclei, except there's a problem here. How are you going to get those two tiny specks, 10 to the minus 5 of the size of the atom, how are you going to get them to ever touch each other? Nuclear reactions are very different from chemical reactions, and they're hard to make go. One way to make them go is to put them at very high temperature and density, like inside a star, where the particles are moving so fast that they just blast. When two nuclei approach, they blast right through the electron clouds, and they overcome proton repulsion, and they actually do touch, and reactions take place. When we do it on the Earth, we usually don't do it this way. We usually use neutrons. Neutrons are like ideal nuclear reaction bullets. And when a neutron approaches an atom, it doesn't care about the electron cloud because it's neutral. It doesn't even care about the protons because it's neutral. And so a neutron, if it could find the nucleus, which is hard because the nucleus is so tiny, but still, if it ever did find the nucleus, it could get in because it's not repelled by anything. So you can make chemical reactions go with only a small amount of matter. And so you've done that with firecrackers and bang snaps. You can make chemical reactions take place. And in our bodies, there are chemical reactions taking place all the time in small quantities, inside cells, which are very small. Nuclear reactions require many kilograms of material because the nucleus is so small. So the neutrons you shoot into a hunk of stuff, they have to go by a lot of nuclei before they find one that they can hit because the target is so small. But it is possible to do it, and you can balance these reactions. It's just like doing chemistry. You just have to watch the numbers on the left and make sure the numbers on the right match up. So if you shot a neutron into lead-206 and it stuck there, what should you get? This is really dumb. So you would get, of course, lead-207. It's still lead. You just put one more neutron in there. Okay, then there's something else that happens. This is a funny thing that happens for nuclei. There's no analog to this with atoms. For some heavy elements, if you shoot a neutron into them, they become unstable. But before they can beta decay their way out of this trouble, they just split into pieces first, and this is called fission. So for example, if you shoot a neutron into a uranium-235 nucleus, it might fall apart into a krypton-97 and a barium-141 and 3 extra neutrons and 173 MeV of energy. That's a lot of energy. And that energy mostly comes out in the neutrons. It always comes out in the light thing. And this isn't unique. It might not be krypton-97. It might be whatever element 35 is, or 34 or 33, and then instead of barium it would be 57 or 58, 59. It's not unique, the pieces they fall apart into. And you get different numbers of neutrons out. But the important thing is that it falls apart, it gives off a lot of energy, and it gives off a bunch of neutrons. Well, notice what it took to get this reaction started. It took a neutron. And now you just got energy out, plus 3 more. Those 3 can now do it 3 more times and make a bunch more energy and make 9. 9 can make 27. 27 can make 81. 81 can make 243, and it just explodes, literally. And this is how you make a bomb. And if you control it so that it doesn't run away and blow up, it's how power plants work. Nuclear power plants, fission power plants. You can also have fusion. It's another way to get energy out of the nucleus. If you take light nuclei and cram them together to make a bigger nucleus, you can also get energy out. Here's a famous example. If you take deuterium, it's hydrogen 2, and tritium, hydrogen 3, and cram them together, you can get helium 4 plus a neutron and 17.6 MeV. This is one of those reactions where you have to have a lot of high energy nuclei to get them to come together, because they've got to overcome the electron clouds. So you need way more energy than several EV. And then you need to have approaching MeV type energies to be able to get the nuclei to get close enough. They actually don't get close enough to touch, but it's a tunneling reaction that takes place that makes this thing go. And per pound, this is about 6 times more energy than fission. So if you're worried about how much something weighs, which you are if you're an engineer, mass costs money. And so this is 6 times better than fission for making energy come out. And the fuel is really abundant. You can get deuterium out of seawater. You can get tritium from a nuclear reactor. You have to work harder at that. And so the fuel is really cheap, almost free comparatively, but the fireplace is really expensive to burn this thing in. They're called fusion reactors, and they don't exist. And we've been working on them for 70 years, and I spent about 10 years of my life working on trying to figure out how to make these things work. And they're just so big and so expensive that it's not clear that any electric utility would ever want to buy one. There's a current international experiment, and that's right, there's only one. There used to be many fusion experiments all over the world. Now there's going to be just one, because it's so expensive. It takes a 10-nation consortium to come up with the money to build it. It's going to be $25 to $35 billion, or maybe more, depending on whose cost overrun estimates you believe. And this thing won't be a power plant. It's just to see what might work. A power plant would presumably be even bigger and more expensive. Or you can use a star. That's the easy way to do it. Just use a star. All stars get their energy from fusion reactions like this. Or you can use a fission bomb to generate enough high temperature to heat and compress the fusion fuel. And that's called a hydrogen bomb, or a thermonuclear weapon. Both of these kinds of ways of getting energy out are based on what's called the curve of binding energy. It's funny, they've taken what we normally think of as binding energy, which is being down in a hole, and for some reason, somebody a long time ago decided to flip it upside down. So the bottom of the well is up at the top, up there where the curve gets to be as high as it goes. And then higher energies are on the right and on the left. And you can see that the ones on the left, there's a lot of energy to be had there between deuterium and tritium in the top of the curve, way more than uranium over there on the right. So fission happens over here on the high end. And when one of these, you shoot a neutron into something that's susceptible to fission over here, it'll split into something that's further to the left on the curve, which means that the pieces are further down in the energy well, and you get a bunch of energy out. Fission is over here. This is what stars do. Stars burn hydrogen to helium, then they burn helium to carbon, then they burn carbon to oxygen, then they burn oxygen to phosphorus, and they just go right up the periodic table until you get to iron. And iron is the end of the line. You can't get energy out. It's at the bottom. And that's where stars, they start approaching iron. They're not getting energy out of fusion reactions anymore. The fire goes out. The star is just hanging there in space with nothing to hold it, no energy source to hold it open. And all the stuff collapses, and it falls, and it falls, and it falls, but it's spherical, it's falling down toward a spherical center point. And when it gets to the center point, and everybody meets, it explodes and splatters itself all over space, and that's called a supernova. You can get electricity from the nucleus. There are two ways. One is fission. We have pretty lousy reactors. They work fine. They generate electricity, but they weren't designed for safety. The first nuclear reactors that were designed to use on ships, submarines, and aircraft carriers. And they had to be made small and put in a confined space down in the guts of a ship. And nobody worried very much with a piece of military hardware about safety. So they weren't built to be safe. They're okay for safety, but we occasionally have accidents and people get terrified. We now know how to build much better ones. We'll see what people want. Fission power is really good in that it doesn't emit greenhouse gases, but they scare people, and environmentalists don't like them very much because of the nuclear waste that they emit, and you have to do something with it. So it's not clear what's going to happen with fission, but it may happen that fission will be part of the mix that we have to go to before we burn the whole planet up. And then there's fusion. It's an almost limitless fuel. This is what we'd like to do, if at all possible, but it's turned out to be practically impossible to use. 70 years we've been working on this, and the joke in the business is that fusion energy is always 30 years away, and has been 30 years away for 70 years. This experiment in France called ITER, International Tokamak Experimental Reactor, won't even generate power. It's just to see what would work. It's going to cost way more than any utility would want to spend on a power plant, and takes so long to build that you couldn't afford to finance it, because it wouldn't start generating any return on investment for 10 years or so. So it's not clear to me that this is ever going to work. Next time, we will continue this theme of what's way down in the tiny part of the atom by talking about elementary particles, and we're going to see how the universe is made. So good luck on the homework, and I'll see you next time.